Thank you very much for the invitation to give this keynote talk at ICSTA 2020. I will be talking about computationally efficient parameter estimation and uncertainty quantification in cardiophysiological systems. This is joint work with various co-authors who I will acknowledge at the end of this presentation. So let me start with the motivation for this talk. Now, in recent years, there have been substantial methodological advancements in the mathematical modeling of complex physiological systems, in particular cardiophysiological systems, which means the mechanics of the heart and the fluid dynamics of the blood vessel network. And on this slide, you see a few books on this topic that have been published recently. Now, if you think of it, that is a really challenging problem because the cardiophysiology of our own body is a much more complex system than most systems that you typically try to mathematically describe in physics, like small molecules or solid states with regular lattice structures. There are no simplifying regular lattice structures in the soft tissues of our body. Now, what most of the textbooks focus on is what is called the forward problem, which you find illustrated here. So here the problem is that you start with a mathematical model and try to understand the characteristics of the data that arise from it. So that includes, for instance, studying the attractor characteristics of your mathematical system, like stable fixed points for stationary data or periodic dynamic cycles to explain potential oscillations in your data. And the kinematic or dynamic equations of a complex physiological system usually don't admit closed form solutions. So we need sophisticated numerical procedures like finite element discretization to numerically solve them. And the mathematical model of a complex physiological system usually depends on a large set of constitutive parameters. So you want to carry out sensitivity analysis to identify those parameters that are associated with your quantities of interest, those parameters that really matter. It's only in recent years that researchers working on complex physiological systems have started to tackle the inverse problem. That is, here we start from the data and ask, what can we learn about the mathematical model from the given data? Now, the challenges here are parameter estimation, uncertainty quantification, and model selection, which you certainly all recognize as familiar topics. In our community, we call that statistical inference. Now, a statistical inference methodology for complex physiological systems isn't conceptually different from standard statistical inference that you all know. However, due to the high computational complexity of cardiophysiological systems, standard statistical inference techniques may not work in practice. For that reason, these techniques need to be adapted appropriately, as I will be discussing in this presentation. The second motivation is more sinister and is related to cardiovascular diseases. Let's look at the United Kingdom, where I live and work, and let's take data from the British Heart Foundation, BHF. Now, according to the BHF, more than a quarter of all deaths in the United Kingdom are related to cardiovascular diseases. That is 170,000 deaths each year. That's 460 deaths per day. Now, 460 deaths per day, that is roughly 10 times higher than the daily mortality rate of patients dying from COVID-19 as of today, 1st of August 2020, when this talk is being recorded. So it is fair to say that cardiovascular diseases are a substantial challenge for the UK health system. It's fair to assume that this applies to other developed countries as well. This leads to the following question. Does mathematical physiological modeling have the potential to lead to better diagnosis, risk assessment, and suggestion of treatment options? So let me start with a review of the forward problem. And this is the work of my colleagues Hao Gao, Xiaoyu Luo, Ray Ogden, and Colin Berry, who are all at the University of Glasgow. So we focus on the left ventricle. That is the heart chamber that pumps oxygen-rich blood into what's called the systemic circuit. That is the blood vessel network that supplies your body with oxygen. Major advancements in this field have become possible as a consequence of the invention of magnetic resonance imaging, which allows us to monitor the heart with its deformation, that is the contraction and relaxation, during the pump cycle. You see a cardiac magnetic resonance scan, or just CMR scan, of the heart, with the left and right atrium on the left and the two ventricles on the right. On the next slide, you will see a video with a time series of CMR scans during several pump cycles. The first task is to extract the left ventricle from the CMR scan. But I won't have the time to go into detail here, but the basic idea is that we apply standard image segmentation techniques illustrated on the left-hand side, where the blue and red rings segment the inner and outer boundary of the vessel wall. The final outcome is a representation of the left ventricle with a mesh, shown on the right-hand side. We take the extracted mesh as a reference time point T1, typically to be taken at early diastole. And the mechanics of the heart are mathematically described by nonlinear coupled partial differential equations subject to certain conservation laws. Now, you don't need to know the details of this mathematical model for the purpose of this talk, but if you want to read up on it, here's a paper written by my colleagues. Now, it is important to point out that the cardiomechanic model depends on various material parameters describing the properties of the heart muscle, the so-called myocardium, for example, related to the stiffness and contractility of the fibers. Now, the cardiomechanic model, combined with its material parameters, defines the kinematics of the heart and allows us to compute the shape of the left ventricle at a later time point T2. And we focus on the so-called passive part of the cardiac pump cycle, also called diastole, going from early diastole, that's time point T1, to late diastole, that's time point T2. The cardiomechanic equations have a closed form solution, so we need to use numerical procedures based on finite element discretization, and they're computationally expensive and require high performance computing. Of interest to the clinicians are the material parameters, as they shed light on the physiology and pathophysiology of the heart and could be used for improved disease diagnosis and treatment planning. Unfortunately, in order to measure them, we have to extract the heart from the patient's body. That means you can only measure these parameters for post-mortem analysis, but not for in vivo clinical decision-making. So the question is, how can we get these material parameters? To describe the heart's kinematics, let's conceptually extract a small cube from the ventricle wall, as shown in the top left, and study its deformation during the heart's pump cycle. As illustrated in the figure, there are three perpendicular deformation modes: the radial mode, the circumferential mode, and the longitudinal mode. So we can now place landmark points on the ventricle wall and observe how they move during the pump cycle. And that is illustrated at the bottom, again with the three perpendicular motion modes. The figure in the top row on the right-hand side shows you the movement of 24 landmark points during the pump cycle. So we now pick two reference time points at early diastole and late diastole and quantify the circumferential displacements for all landmark points. These displacements are called strains. These strains can be extracted from the CMR scans. Now, we only extract circumferential strains, as longitudinal and radial strains are much more difficult to extract at a reasonable level of accuracy. Now we obtain the CMR scan from a patient. From the CMR scans, we extract the circumferential strains for the landmark points, and we also extract the cavity volume of the left ventricle at end of diastole. Then we use the mathematical model to predict the same features, the 24 circumferential strains and the left ventricle cavity volume at end of diastole. Just remember that these predictions depend on the material parameters. Next, we quantify the mismatch between the features extracted from the magnetic resonance image scans and those predicted by the mathematical model. And we then want to find the parameters that minimize the mismatch, which means the parameters that give us the best agreement between the data and the predictions from the model. We quantify the mismatch by the residual sum of squares between the features extracted from the CMR scans, here shown in blue, and the simulated features, that is, the predictions from the model, here shown in red. V refers to the left ventricle volume at end of diastole, and we divide by the measured volume to non-dimensionalize this quantity. The epsilons refer to the circumferential strains, which are already non-dimensionalized. Now, the obvious question to ask is, how useful are these biophysical material parameters? How will they aid a clinical practitioner? And remember, these are the parameters on which our cardiomechanic model depends. To test that, we looked at STEMI, which is a particular form of myocardial infarction or heart attack. We obtained magnetic resonance image scans for 11 STEMI patients and 27 healthy volunteers as controls. Now we want to predict the disease status, that is, STEMI versus healthy control, from the CMR scan, but we obviously can't work with a high-dimensional pixel space of the image directly. So a standard approach is to apply some statistical dimension reduction technique and then build a classifier on this dimension-reduced space. And our idea was to use the material parameters for dimension reduction, which means to map the high-dimensional image space onto the low-dimensional space spanned by the material parameters. We obtained a sensitivity of 75% and a specificity of 95%, which clearly indicates that the material parameters are highly relevant for disease diagnosis. The details are reported in the paper shown at the bottom, published in the Journal of the Royal Society Interface. So rather than relying on their intuition when interpreting magnetic resonance image scans for disease diagnosis, clinical practitioners could in principle use an automated clinical decision support system based on these material parameters for automated and more objective risk assessment and disease diagnosis. However, there's a fly in the ointment in that the mathematical model of the cardiomechanic processes doesn't admit closed-form solution. What we have to do is use numerical procedures based on finite element discretization. This is illustrated here with the discretization of the left ventricle wall with a mesh of finite element nodes. The practical solution of these finite element equations takes about 10 to 50 minutes on a high-performance computer. Now remember that we want to minimize the mismatch between the predicted and measured circumferential strains and the left ventricle cavity volume. And this mismatch is a function of the biophysical material parameters. So this optimization problem doesn't have a closed-form solution either, so we have to use iterative optimization techniques. This is illustrated here for the hypothetical scenario of two material parameters. In fact, we have more than two parameters. Depending on the cardiomechanic model, we typically have 4 or 8 parameters, but we cannot draw a 4-dimensional space. So for illustration purposes, you see two constitutive parameters here on the horizontal axis, and our mean square objective function is shown on the vertical axis. We now want to use an iterative optimization technique. This is illustrated here, and this could be conjugate gradients or quasi-Newton with multiple restarts, or some global optimization algorithm. And the upshot is that this will require repeated numerical solutions of our finite element equations each time we change the material parameters as part of the iterative optimization routine. That can be hundreds or thousands of times, depending on the complexity of the objective function. This leads to very high computational costs overall. In fact, the computation for the study reported earlier took about 3 weeks on our high-performance computing cluster. Now imagine a critically ill patient comes into the A&E department. Clinical practitioners ask you to help them with the medical diagnosis, and you tell them that you first have to estimate the parameters of your cardiomechanical model, and then they should come back 3 weeks later. By that time, the patient may be dead. So the upshot is that we cannot use the mathematical model and parameter estimation procedure I've just described for clinical decision support. So let's now try and find a way to get the mathematical model into the clinic and look at the inverse problem. We have already started looking at the inverse problem, but let's now try and do it in a way that is viable in the clinic. With this joint work with my former PhD students, Umberto Noi and Vinnie Davies, my current PhD students, David Dalton and Ellen Lazaros, and my postdoc, Agnieszka Borowska. A mathematical model is an abstract representation of the real world, and a numerical solution of the mathematical equations, which we call the simulation from the model, is much faster than doing a complex physiological experiment. However, it isn't fast enough. For that reason, we need a second level of approximation and replace the computationally expensive mathematical model by a computationally cheap statistical surrogate model. We call that emulation. The statistical surrogate model is our emulator. Now, the idea of emulation isn't new. Groundbreaking work has been done by Tony O'Hagan and his group, and here is one of his seminal papers on this topic. So let me give you a two-dimensional illustration. Let's assume we have two material parameters. In fact, we have a high-dimensional parameter space, but in order to be able to illustrate this procedure, we have to restrict that to two parameters. Let's also assume we want to emulate one circumferential strain. As you know, we have in fact 24 circumferential strains, but I wouldn't be able to draw this. Now, we cover the parameter space with some space-filling design, and for each parameter vector from this set, we run a forward simulation from the model. That is, we solve the finite element equations. Now, if the parameter space were discrete, we would now have a lookup table that we could refer to in the clinic. That is, we would never have to run the computationally expensive forward simulations when a patient is admitted to A&E. However, the parameter space is not discrete. And because it's not discrete, we need to fill the space in between with some smooth nonlinear interpolation. Now, let me give you an illustration. We use an 8-parameter model, the so-called Holzapfel-Upton model. But for illustration purposes, to be able to draw this, let's assume that 6 parameters are known and fixed, and that 2 parameters have to be learned. This figure shows you contour plots of the objective function, that is, the residual sum of squares quantifying the mismatch between the data and model prediction as a function over the two-dimensional parameter space. On the left-hand side, you see a contour plot for the simulator, that is, the direct numerical solution of the finite element equations of the original mathematical model. On the right-hand side, you see the corresponding plot for the emulator. You see that the functions are similar, and the parameters that we get from the optimization of these functions are also similar. However, the optimization of the function on the left using the simulator takes several hours, while the optimization of the function on the right, the emulator, only takes a few seconds. However, we now have to address the problem of how to do the interpolation in parameter space. Well, the method that we use is Gaussian process regression, which here is an excellent textbook on this topic by Karl Edward Rasmussen and Christopher Williams. In this talk, I only have the time for a brief intuitive introduction to Gaussian process regression. This is based on lecture slides by Mark Deisenroth. So let's assume that we want to learn a function from some data. We know that the data have been standardized to zero mean and unit variance. So we expect the function to be focused on the shaded area. We also expect the function to be smooth, and we can get a draw of functions from the prior distribution. In fact, that's what a Gaussian process is. It is a prior distribution in function space. Now, we get our data by running the mathematical simulator for a few parameters. This is illustrated by the crosses. The parameters are the inputs to our function, so they are represented by the horizontal axis. So conceptually, what we want to do is keep all those functions from the prior that go through these crosses and discard the others. This will give us a sample from the posterior distribution, and we can then get the posterior mean and the posterior variance directly from the sample. Now, in principle, you could easily implement this procedure with rejection sampling. That would be computationally very expensive. The good news is that for Gaussian processes, we don't have to do this numerically with rejection sampling, but we can do this analytically and get closed form equations for the posterior mean and the posterior variance. The advantage of Gaussian processes over alternative methods, like splines, is that we can get and do exact interpolation rather than just regression. And that is what we conceptually want to do, exact interpolation, since the mathematical model is deterministic. We use the Gaussian process posterior mean for our interpolation. And we have two different emulation strategies that we can follow. Just a reminder that our objective function, which means the function that we want to minimize, is a residual sum of squares over 24 circumferential strains in the left ventricle cavity volume at end of diastole. One emulation strategy is to build 25 separate emulators for each of the 24 circumferential strains and for the left ventricle cavity volume. An alternative emulation strategy is to target the objective function directly and only construct one emulator for the objective function. So the question is, which of these two emulation paradigms is to be preferred? To answer that question, we run a simulation study. We first cover the parameter space with 10,000 points generated from a Sobol sequence to give us a space-filling design. Loosely speaking, this means that our parameter space is covered uniformly. Now, each of the points is a vector of material parameters, which we insert back into the cardiac mechanic model and solve it numerically with finite element discretization. Recall that we refer to this as simulation. Each simulation will give us the outputs in the form of 24 circumferential strains and the left ventricle cavity volume at the end of diastole. We can now either use these outputs directly to construct output-specific emulators or combine them into the objective function and construct an emulator for this objective function. Now recall that the computational costs of a single simulation with finite element discretization are in the order of 15 minutes. So the total costs are 10,000 times 15 minutes. That is approximately 100 days. However, this doesn't have to worry us. Firstly, the simulations can be parallelized. And secondly, in a real application, these simulations would be carried out before the patient comes into the clinic. In fact, before our model would ever be used in the clinic. So they are of no concern to the clinical practitioner. We now want to mimic what happens in the clinic where patients' MRI scans are taken. We extract the relevant features from these scans. Again, these are the 24 circumferential strains and the left ventricle cavity volume at end diastole. We now want to obtain the corresponding material parameters. To mimic this, we continue the Sobol sequence to get 100 new material parameter vectors in an out-of-sample test set. This corresponds to 100 new patients who haven't been seen before and whose data have not been used for constructing the emulator. We then want to use our emulator to estimate these material parameters. Here are the results of our study. In the table, you see two rows denoted output and loss. Output stands for output emulation, where we have 25 separate emulators for each of the 25 features extracted from the magnetic resonance image scans. Loss is just another name for objective function. This is the approach where we build one emulator for the objective function. The numbers in the table show you the distribution of mean square errors between the estimated and true parameters. The distribution is over the 100 cases in the out-of-sample test set. This corresponds to a distribution over a patient population of size 100. The distribution is summarized by the median and the first and third quartiles. You can clearly see that the mean square error values when using the first emulation strategy, where we have 25 emulators for each of the magnetic resonance image features, are reduced by 3 orders of magnitude. This is quite a substantial improvement. So our finding is that we should use the first emulation strategy and build an emulator for each of the features or outputs, and then use these emulators to compute the objective or loss function, rather than emulate the objective or loss function directly. You find more details on this study, as well as the investigation of various other emulation strategies in the following paper with the title Fast Parameter Inference in a Biomechanical Model of the Left Ventricle by Using Statistical Emulation, which was published in the Journal of the Royal Statistical Society, Series C, on Applied Statistics last year. And the next question is, how do we take the posterior standard deviation into consideration for uncertainty quantification? Our objective function is the residual sum of squares between the data yi and the model prediction zi. Now recall that the data yi are the 24 circumferential strains and the left ventricle cavity volume at end of diastole extracted from the magnetic resonance image scans. The predictions depend on the material parameter vector theta, which we want to learn, They also depend on the left ventricle geometry H, as I will be discussing later in this talk. Well, let's assume that the data are subject to Gaussian IID noise, that is Gaussian independent and identically distributed noise. Now, it is straightforward to show that minimizing the residual sum of squares objective function is the same as maximizing the conditional log likelihood, conditional on the model prediction Z. You see that the term on the left is just the residual sum of squares multiplied by a term that depends on the noise variance. And the term on the right is constant for no noise variance. So this is the objective function that you would aim to maximize when using the original mathematical model, that is, the simulator. Now, when using the emulator, we need to allow for the fact that Z itself is subject to uncertainty, as shown in the figure at the bottom. So what we have to do is integrate Z out. Now, this leads to a Gaussian convolution integral. The term in blue is just the Gaussian noise term. The term highlighted in yellow, that is the Gaussian distribution coming from the Gaussian process. MUI is the posterior mean, and sigma I square is the posterior variance. And both depend on the material parameter vector theta. They're also dependent on the left ventricle geometry H. Now, the Gaussian convolution integral has a closed form solution, which is shown in the equation at the bottom. And this equation has quite an intuitive form. You see that the residual sum of squares term on the left has the posterior variance of the emulator as an additional additive term in the denominator. So this means that those areas in the parameter space where the emulator predicts high uncertainty are downweighted. So if you take as an example the graph at the bottom, you see that areas in the parameter space to the right of the value 2 are downweighted due to the high posterior variance of the emulator. In this presentation, I will discuss an application to real cardiomagnetic resonance scans from a healthy volunteer. Now, because it's a real application, the true parameters are unknown. So we use the mathematical model with a numerical procedure based on finite elements as a surrogate gold standard, and refer to that as the literature values. That's taken from the paper that you see at the bottom of this page. Just recall again that the objective of emulation is not to get better results than with the original simulator, but to get them faster. So our objective is to improve computational efficiency without sacrificing accuracy. Now, as we've discussed before, we can see the deformations of the left ventricle during the pump cycle with MRI. And we can mathematically describe this deformation between two reference time points, like early and late diastole. We call that the strain. And what we can't get from the MRI scans are the forces acting on the tissue, called stress. Now, for given cardiac mechanics parameters, we can compute the stress, that is the forces, from the stretch, that is the deformation. And that is of interest for clinical diagnosis to plot the stress as a function of stretch along different directions in the myocardium, that is the heart muscle. And recall again that this stress-stretch relationship depends on the cardiac mechanic parameters. Here you see two stress-stretch curves for two different stretch directions, the sheet direction on the left and the stretch along the myocytes on the right. In both panels, you see three curves. The blue curve shows the stress-stretch relationship from our emulator. The black dashed line shows the corresponding curve from the literature obtained with the original simulator, and the red line shows the difference. As you see, the two curves for the simulator and the emulator completely overlap, and the difference is 0. We have to magnify the scale on the vertical axis by a factor of over 100 to see any difference. Here, the blue line shows the difference between the curves obtained from the emulator and the simulator. And the vertical bars show 95% confidence intervals obtained with residual bootstrapping. You can also get the Bayesian credible intervals with an approach based on running MCMC on the emulated log likelihood surface, which gives very similar results. The upshot is that the 0 line is included in the intervals most of the time, suggesting that the emulator is an excellent approximation of the original simulator from the literature. However, the computational costs have been reduced from over a week, as required for the original simulator, to less than 50 minutes, which is an improvement by about 3 orders of magnitude. This is an important stepping stone towards getting the cardiomechanic models into the clinic and integrating them into a clinical decision support system. You can find more details in this paper published last year in the Journal of the Royal Society Interface. However, our previous work was based on the left ventricle from one particular healthy volunteer. The emulator was built with this left ventricle geometry for the reference time point T1 at early diastole fixed. If we want to build an emulator that is useful for the clinic, we need to allow for the fact that every person has a different heart and that the left ventricle is different from patient to patient. So we need to extend our previous work by including the left ventricle geometry as an additional input to the emulator. This is joint work with my PhD students Ellen Nazaros and David Dalton, my postdoc Agnieszka Borowska, and my former postdoc Lukasz Romastro. Now, the left ventricle is represented by a mesh of about 17,500 element nodes. Mathematically, that's a 17,000 dimensional vector. There is no way that we can build an emulator or such a high dimensional input space. So what we need is some form of dimensional reduction. Now, the simplest approach is based on principal components analysis, or PCA, which is illustrated in this diagram. Let's assume we have a population of points in 3-dimensional space, that is a population of 3-dimensional vectors. We are only allowed to represent each vector with a single number. What would you do to minimize the information loss? Well, the simplest idea is to obtain the leading principal component, shown here by the red dashed line, and project each 3-dimensional point via orthogonal projection onto the line spanned by the principal component. Now, if we have a population of left ventricle meshes, illustrated on the right-hand side with the different green shadings, this works in principle in the same way, except that the dimension is higher, 17,000 rather than 3, and that we use more than just one principal component. A disadvantage of PCA is that we are restricted to a projection onto linear subspace. To allow for more flexible, smooth, nonlinear manifolds, we can use more advanced machine learning methods like autoencoding neural networks. In the autoencoding neural network, we map a high-dimensional input vector to a high-dimensional output vector via a low-dimensional bottleneck layer for dimensional reduction. We present the left ventricle at the input layer. The neural network presents the left ventricle at the output layer. And we then apply a properly regularized backpropagation training scheme to adjust the parameters of the neural network such that we have maximum agreement between the left ventricles at the input layer and the output layer. And we can now obtain the low-dimensional representation of the left ventricle from the inner bottleneck layer. We tested these two schemes using the left ventricles from a mixed population of 198 healthy volunteers and myocardial infarction patients. We compared the reconstruction accuracy between PCA and the neural network autoencoder in terms of mean square error between the left ventricles at the input and the output layer. And we did the evaluation via a leave-one-out cross-validation scheme, which means we trained on 197 left ventricles and then assessed the reconstruction accuracy for left ventricle that had been left out of the training set. Then we cycle through the whole set of left ventricles, and so on. The following scatter plot compares the 198 out of sample reconstruction errors between PCA, shown on the horizontal axis, and the neural network autoencoder, shown on the vertical axis. The neural network autoencoder was trained twice for 2 different transfer functions, and that is represented by the 2 different colors, red and blue. And as you see, there's no significant difference in performance between the neural network autoencoder and PCA. And so we use PCA because it is computationally much cheaper than training a neural network autoencoder. We also included a comparison with a parametric model from the cardiomechanics literature, which was easily outperformed by PCA. When deciding on the number of principal components, we need to carefully trade off the reconstruction error versus the emulation error. The plot on the left shows a distribution of reconstruction errors over the 198 left ventricles for different numbers of principal components. As you would expect, the reconstruction error monotonically decreases as the number of principal components goes up. However, as the number of principal components increases, the dimension of the input space increases too, and so the emulation error will get worse. From the graph on the left, we can see that the improvement in the reconstruction error from 5 to 6 principal components is fairly modest, and we therefore decided to project the left ventricle onto a space spanned by the 5 leading principal components. In this figure, you see a comparison between the original left ventricle mesh, shown in red, and the reconstruction via projection onto a 5-dimensional PCA space, shown in gray. The 2 different gray shadings represented 2 different walls, the inner and the outer wall. And here's another example of the same for a different subject from the population. Let's now look at the stretch stress curves again for 2 different stretch directions. As before, we compare the stretch stress curve obtained from the original simulator, shown in red and called true curve, with the stretch stress curve from the emulator, shown in blue. We also quantify the uncertainty with a Bayesian analysis as follows. We run MCMC simulations on the emulated log likelihood to sample material parameters from the posterior distribution. We then compute the stretch stress curve for each parameter in the posterior sample to obtain a posterior distribution of stretch stress curves. From that distribution, we obtain the 95% credible intervals, which is shown by the gray shading. We see that the agreement between the emulator and the original simulator is not as good as before, when the left ventricle geometry was known and fixed. However, it is still reasonable in that the stretch stress curve for the simulator lies inside the 95% credible interval of the emulator. And here's another example for a different subject from the population, which gives us qualitatively the same result. We're currently working on trying to improve the performance by systematically including prior knowledge related to cardiophysiological ex vivo data. And this joint work with Alan Lazarus, Jiayu Luo, and Hao Gao. And it is based on a study reported in the following paper by Stefan Klotz and co-authors. The authors studied for a large population of ex vivo human hearts the relationship between the blood pressure and the normalized left ventricle volume. The figure shows the author's original data. At the top, you find the empirical law that the authors found, and the solid line shows the fit of this law to the empirical data. In our work so far, we've only tried to estimate the cardiomechanic model parameters from in vivo data in the form of magnetic resonance image scans. We now want to put a prior distribution on the cardiomechanic model parameters based on the empirical Klotz curve law and ex vivo data. We follow the Bayesian analysis described before, based on running MCMC simulations on the emulated log likelihood surface to get the posterior distribution of stretch stress curves. We then get the stretch stress curve from the original simulator, which we call the true stretch stress curve, and compute the median posterior probability density of this curve. This is repeated for 6 healthy volunteers. The 2 panels show 2 different stretch directions. The 2 colors refer to the Klotz curve prior, shown in blue, and an uninformative prior, shown in red. And the vertical bars represent the spread over the 6 healthy volunteers. We see that with the Klotz curve prior, we get systematically higher posterior probabilities, indicating a better agreement with the true stretch stress curve. The tick symbols at the bottom indicate that the difference is statistically significant. The following figure shows a contour plot of the log prior distribution from a simulation study where all material parameters were kept fixed, except for 2 of them, called θ2 and θ3 here. Now, θ2 is a parameter with a high sensitivity index. That is, this parameter is easy to infer from the data. On the other hand, θ3 is a parameter with a lower sensitivity index, which means this parameter is difficult to estimate from the data, or to put it differently, it always has large intrinsic uncertainty. The figure shows that conditioning on θ2 reduces the uncertainty in θ3 as a consequence of the Klotz curve prior. We investigated the effect of the Klotz curve prior in a further simulation study using the left ventricles from 6 healthy volunteers, denoted here by G1 to G6. The figure shows you the posterior distributions of the squared errors between the true and estimated parameters for the critical parameter θ3. The gray boxes show you the posterior distributions obtained with an uninformative prior. The white boxes show you the posterior distributions obtained with a Klotz curve prior. A comparison of these distributions suggests that we get a clear reduction of both the bias and the variance when using the Klotz curve prior. So let me conclude. Cardiac mechanic modeling holds great prospects for improved cardiac disease diagnosis. However, to make clinical decision support viable, statistical emulation is essential. For a fixed left ventricle, we managed to speed up inference by 3 orders of magnitude at negligible loss in accuracy. When including the left ventricle in the emulator and using dimensional reduction with BCA, the simulator and the emulator were found to be in agreement within the predicted posterior uncertainty. And preliminary results for integrating prior knowledge based on population-wide ex vivo data are promising. This work has been funded by the Royal Society of Edinburgh, reference number 62335, and it has been carried out as part of the SoftMag Research Center, funded by EPSRC under their Mathematics for Healthcare initiative. And this is the end of my talk, so it's now over to you to ask me any questions that you may have.